All
right, let's start with this question. So here's a question of the day.
Yeah. But here, like, we'll wait. Show up.
Go for it. You have 2 minutes. This is a non-calculator question. That's what we did yesterday. Anybody have an answer yet?
C.
C. Anyone else get C? Anybody have a different answer? You want me to give you another minute? Okay, I'll give you another minute. Maybe it's C.
Yeah, I don't know what else says anything. It's just scary, but it's fine.
Okay, so the first thing to understand about this problem is this is a rate function that they're giving us. And remember, if you take the definite integral of a rate function, it gives you the total amount of change of the quantity that the rate is of, right? So in this case, if we wanted the number of gallons, right, it's going to be the definite integral from 0 to 9 of R of t. This is going to be the number of gallons after 9 minutes, right? It's the total change in the number of gallons. So if we start with an empty tank, wait, we're not. We're starting with 15 gallons, right? So it's going to be 15 plus that, right? Does everybody understand that? We're starting with 15 gallons. This is FTC part one. Yeah, written a different way, right? So if we take the initial amount plus the amount of change in the number of gallons, we get the number of gallons after 9 minutes. Okay, so the answer is going to be 15 plus the integral from 0 to 9 of R of t dt. But they're saying approximate that definite integral using a trapezoidal sum. So this is going to be approximately equal to 15 plus L gram plus R gram divided by 2. Right? So this ends up being a lot of writing. 15 plus, it's going to be, the L ram is going to be the height of the rectangle at the left-hand endpoint, which would be 9, times its width, which is going to be 4. difference of the x values, or the t values, plus 6 times 3, plus 4 times 2. Right, that's the LRAM part. Plus the RRAM part would be 6 times 4, plus 4 times 3, plus 3 times 2, all divided by 2. And then you have to do this out without using a calculator, which is sort of a pain in the neck. 15 plus, this is 36, plus 18, plus 8, plus 24, plus 12, plus 6, all divided by 2. I think it seems easier to just cut each of these numbers in half and then do the sum. That seems easier to me. So this would be 15 plus 18 plus 9 plus 4 plus 12 plus 6 plus 3. And then add them up. So this is 33, 42, 46, 58, 64, 67. Perfect. Does that make sense? That problem probably took me a little longer than 2 minutes. So, you know, you get credit on some problems. Like if you look at the problem just before this, scroll up. If you look at the problem just before this, it was find the derivative of that function. That should be like super quick. So you get a little credit on that one to use on the next problem. A limit, again, it shouldn't take very long. So I mean, it's gonna take you a little longer to do certain questions and a little less time to do other questions, but you know, try and really make sure that you don't make a mistake. I guarantee you they had a choice for people who didn't realize that there was water in the tank to begin with.
Yeah, that was the first choice.
Because that's the mistake I made. Right? I'm sure, like if I was writing this question, I would definitely put 52 on there. Okay? All right, any questions on that? All right, so yesterday we talked about Riemann sums. Everybody okay with that? It's just adding together rectangles of different heights, right? So sometimes they'll use left-hand endpoint for the height of the rectangle. Sometimes they'll use the right-hand endpoint. Sometimes they'll use the midpoint. And then this trapezoid sum, which is just the average of the left and right. Any questions on it? Not too bad, right? Okay, so I just wanted to do a little bit of a review on summation notation. So I'm not sure when you learned this, maybe algebra 2?
Yeah.
I don't really know. But it's just that capital sigma, Greek sigma. So just a reminder here. So remember, you have a capital Greek sigma, right? Sometimes they'll have stuff on top about it, like it'll be like k equals 3 to 5 of k squared, or something like that. Okay? This letter k is sometimes called the index of the summation. The 3 is the starting point. The 5 is the ending point. So all you're going to do here is you're just going to start with 3 and plug it in for k. So 3 squared. Plus, and then you go to the next consecutive integer, 4. Plug that in, 4 squared. Plus, and then you go to the next consecutive integer, 5 squared. And then you go to the next one and the next one until you get to the ending point. So here we would stop. So this just ends up being 9 plus 16 plus 25. So the answer would be 50. Right? You all remember doing that, right? So we can actually express Riemann sums using summation notation. That's what tonight's homework is about. So Riemann sums using summation notation. For example, suppose we have the function y equals x squared. Okay, so y equals x squared, like that. And we want to approximate definite integral from like 1 to 3. Suppose that's the area we're trying to approximate. Area from 1 to 3. Definite integral 1 to 3 of x squared dx. So say I wanted to approximate this using the right rectangular approximation method with, let's say, 8 subintervals of equal width. All right, so what does that mean? That means that I'd have to actually split this up. Each one unit would have to be split up into fourths, right? So you'd have to split that up into fourths, and then for each width, I'd have to make a rectangle using the right-hand endpoint as the height of that rectangle, right? It's like we did yesterday, right? So if I wanted to write that using summation notation, I could say this is the sum of k equals 1 to 8. I'm summing together 8 rectangles, right? The height of each rectangle, let's see, it would be something squared. Like the first one, I want it to be 1.25 squared. And the second one, I want it to be 1.5 squared. And the next third one, I want it to be 1.75 squared. And then 2 squared, and so on, right? So I could think about this. I could just take 1 plus like 0.25 times k squared, right? Because in the first rectangle, I want it to be 1.25, which is 1 plus 0.25 times 1. The second rectangle, I want it to be 1.5. That's 1 plus 0.25 times 2 squared, and so on. This would work, right? That gives you the height of the triangle in each case. And then the width of the triangle in each case is always 0.25. So there, I wrote this as a summation. I wrote the right rectangular approximation method using 8 subintervals as a summation. That's not too hard, right? I mean, it could be a little more complicated. Like, what if it was something crazy like trig? What if it was sine x between 0 and pi? That's the area I'm trying to approximate. And I wanted to use, again, right rectangular approximation method with 20 subintervals. Right? So that would be summation. K equals 1 to 20. So there's 20 rectangles I'm adding up. Of sine something. Okay, so what's that something going to be? Well, what's the width of each triangle going to be? Or each rectangle, rather, going to be? Pi over 20. So I just want to take the sine of pi over 20 times k. That wasn't too hard, right? Even though it was a weirder function and more subintervals, it's still pretty easy. The width of each rectangle, pi over 20. There, I'm done. That was kind of easy. Let's do a harder one. I thought that one would be harder. It's not. Okay. So what if I just took, what if I wanted to estimate the integral from 3 to 7 of x cubed minus 2x plus 1 x using the right rectangular approximation method with, let's say I wanted to have 40 subintervals. All right, I'll do the hard part. Summation k equals 1 to 20. You guys can do the easy part. What's the total width of the interval that I'm trying to integrate over? It's 4. The width of the interval is 4. You get that by just subtracting, right? So what's the width of each rectangle have to be then? 1/10. Okay. So this is going to be, I want to start at 3, but I want to add 1/10 each time, right? So it's going to be like 3 plus 0.1k cubed minus 2 times 3 plus 0.1k plus 1. That's like the height of the rectangle each time. Does everyone agree with that? So the first time around, I'm going to evaluate this function at 3.1. Second time around, I'm going to evaluate this function at 3.2. Third time around, I'm going to evaluate it at 3.3, and so on. Yeah.
Does it end at 20 or does it end at 40? I don't
It's 40. I did the easy part. I just said it was the hard part. Joking around, and I messed it up. Thank you.
Yeah.
Stupid. All right. Am I done? Yeah, multiply by 0.1. There. That still wasn't that bad, right? I mean, I could do any of these with a right rectangular approximation method. What if it was left? What would be different in this problem? Or in that problem? Or in that problem? What would be different if it was left rectangular approximation method? Not a lot.
Start at 3. That's 3.
Yeah, exactly. That's all I would need to change. I just go from 0 to 39. Because then the first time around, you're evaluating at 3. The last time around, you're evaluating at 6.9, right? So that would definitely work. Good thinking. Everybody okay with this? This isn't so bad, right? All right, so let's just make a general thing here. So what if it was just generally random squiggle curve f of x from A to B? And I want to approximate this area using R ram with n subintervals. Any number. N could be any number. Well, okay, so the first thing is it's going to be the summation k equals 1 to n. The height of the rectangle is always going to be f of something. And that something is going to be a plus, right? I want to start at a. So a plus the width of the rectangles times k. How do you get the width of the rectangles in this case?
E minus A over.
Yeah, exactly, right? So if I have a random rectangle here, right, then this width right here has to be b minus a, which is the total width, divided by the number of rectangles, right? So it's going to be a plus b minus a over n times k times b minus a over n. That's like the general formula for this. The function will be different each time, but you just do this to it every time. That's not so bad, right? Okay, since that's all I have to talk about today, but since we have a little extra time, I wanted to address Paul's question, even though Paul's not here. But hopefully he'll watch this and he'll get the answer to his question. He asked the question, and I'm sure several of you were thinking the same thing. When I first started talking about areas and definite integrals, I said that the area under the curve is actually equal to the definite integral. And it's like, what? How's that true? So I just want to talk about, like, intuitively how you can think about how we get from areas to like antiderivatives, which seems sort of unrelated, okay? So let me just talk about that for a second and then we'll be done. So I was trying to think about how to explain this, and this is kind of what I came up with. Nobody's ever questioned it when I said it before. So I was like, oh, yeah, that's a good point. I wasn't quite sure. So, but I thought about it and I came up with this. So suppose you have this function f of x, okay? Whatever, it could be any function, f of x. And let's just define a new function to be the area under the curve from 0 to something, okay? Like, for example, if I have this x value right here, let's say that this area right here is a of x. Okay? Well, in this case, all right, suppose I have another little sliver of area right here. Okay, and this x value right here is like x plus a little bit, x plus h. Right? Then if I wanted to calculate this area right here, it would really just be a of x plus h minus a of x. Right? Don't you think? So this area right here is equal to a of x plus h minus a of x. But we know that we can actually approximate that area by using a rectangle, right? We can say this is approximately equal to the height of the rectangle, which let's just say that's f of x, right? We'll use the left-hand endpoint, times the width of the rectangle, which is just h, right? This makes sense so far, right? Nothing I've said is like totally strange. But hopefully you agree that as h gets smaller and smaller, this is closer and closer to being true, right? Not an approximation, but an actual amount, like equality. So I could express that as a limit, right? I could say that as the limit as h goes to 0 of a of x plus h minus a of x. Let's divide by h equals f of x. Right? I could divide by h, that's no problem. It's not 0, it's an amount. All right, so does this look familiar? What is this? This is the limit definition of derivative. This right here is really a prime of x. So a prime of x equals f of x. Following me so far? So I'm saying the derivative of area is the function. Well, another way of writing that is the area is the integral of the function. Now, the actual proof of this is way more in the weeds, and I don't think it's worth going there. But this gives you sort of an intuitive understanding of how you get from area to antiderivatives, because we got from area to derivatives, so then you can get to antiderivatives just by integrating. Is that satisfying? Do you kind of understand, just the basic thing? I mean, you don't have to be able to prove it or anything like that. You just have to believe it. So I want to make sure you believe it. The definite integral is definitely the area under the curve. Okay? Any questions about that?
So with the integral of an area, can you do that?
The integral of an area?
Say you have, say you have an equation that's an area, and then you want to
Not feeling.
Well, if you take calculus 3 in college, you can talk about double integrals and things like that. So yeah, that's a thing, but again, it's like a little past where we are. So it'd be better to not try and stress over it for now. But it's a great question. You guys have great questions. That's why I just love this class. You guys are my favorite class ever. It's true. I've been teaching for like 23 years. My favorite class ever. When you have a class full of students who ask good questions, it just makes me a better teacher. So I think I like it better. When I have a class where nobody cares and they all suck, it makes me suck. All right, I'm gonna stop recording now. You don't have what I'm saying.